Let's take a look at the fastest manned aircraft ever.
Ready to launch now.
The Hypersonic X-15.
Good light.
The North American X-15 was an experimental Air Force and NASA hypersonic, rocket-powered aircraft that was used to investigate materials, aerodynamic design, and control systems associated with high-altitude boost and reentry. Launched from an NB-52 mothership, the X-15 would engage its rocket motor and perform what was then termed a space leap, leave the atmosphere, enter the fringes of outer space, and perform a reentry. Over 50 years later, the X-15 still holds the speed record as the fastest man-powered aircraft, Mach 6.72. And in case you're wondering, hypersonic flight is defined as greater than Mach 5, and during this time an altitude of 300,000 feet or 91,440 meters was defined as the point where aerodynamic effects were near zero and space began. Notable features of the X-15 include small trapezoidal wings, landing skids, and a wedge-shaped tail. Let's take a look at some specifications of the X-15. Length: 50 feet 9 inches or 15.47 meters. Height: 13 feet 3 inches or 4.04 meters. Wingspan: 22 feet 4 inches or 6.81 meters. Wing area: 200 square feet or 19 meters squared. Engine: 1 Reaction Motors XLR 99 RM2 liquid-fueled rocket engine. Variable thrust from 15,000 pounds or 66.72 kilonewtons to 57,000 pounds or 253.55 kilonewtons. Maximum speed: Mach 6.7. Demonstrated service ceiling: 354,330 feet or 108,000 meters. Thrust to weight ratio: 2.07. Although most aviation enthusiasts associate the X-15 with the dry lake runways at Edwards Air Force Base in California, the origins and design of the X-15 actually come from the East Coast and predate even NASA. Before NASA, there was NACA, or the National Advisory Committee for Aeronautics, and the genesis of the X-15 begins with NACA at the Langley Research Center in Hampton, Virginia. Back in 1952, a memo from NACA headquarters entitled Research on Spaceflight and Associated Problems was sent out to Langley. The memo asked for, quote, increase its program dealing with problems of unmanned and manned flight at altitudes between 12 and 20 miles and Mach numbers between 4 and 10, end quote. And although there had already been informal research in the realm of hypersonic flight before the 1952 memo, it became more of a priority following that communication. Initially, the plan was to use the Bell X-2 research plane, strapped with 2 JPL-4 Sergeant boosters, and launch it from a carrier aircraft. But after extrapolating the X-2's flight data, it was found that aerodynamic control would be weak at Mach numbers over 2.0. Additionally, the initial researchers felt that the biggest design challenge would be the excessive structural loading caused by acceleration during re-entry, and not aerodynamic heating of aircraft surfaces. Ultimately, the use of X-2 with boosters and the assumption that structural load forces were the biggest challenge would both prove to be incorrect. By 1954, NACA recommended that a new research airplane be developed which would have higher speed and altitude capabilities than anything flying. The request was sent out to 3 national laboratories: Ames in California, Lewis in Ohio, and Langley in Virginia. And while research began at all the laboratories, Langley had an edge, a secret one. Back in 1945, a NACA engineer named John V. Becker, himself a veteran of the X-1 project, had developed an 11-inch hypersonic wind tunnel. Initially, the tunnel was so secret that it was identified only by the nondescript designator, Project 506. The hypersonic tunnel was instrumental in understanding the shock layer boundary interaction and would prove to be the primary aerodynamic research tool to develop the X-15. Becker's team had its work cut out for them. They were only given 4 weeks to perform the initial study and 3 years to produce a flying example. By comparison, the X-2 program took 10 years to produce a prototype. Given the tight timeline, each person on the team would handle their own specialty, with Becker assigning himself the challenge of designing an aircraft skin that could withstand the extreme temperatures of re-entry into the atmosphere. It was found that a maximum skin temperature of 1200 degrees Fahrenheit or 649 Celsius could be sustained if the panels were manufactured using a nickel-chromium alloy known as Inconel X. Using this material, it was calculated that a speed of Mach 6.3 could be reached if the aircraft was dropped from a B-52 at 35,000 feet or 10,668 meters. Having solved the heating problem, the next design challenge was maintaining stability at very high speeds. Just before the development of the X-15 began, Chuck Yeager had flown the X-1A to a maximum speed of Mach 2.44. During that flight, the aircraft began to develop lateral oscillations and lost over 50,000 feet of altitude before Yeager could recover the airplane once the speed went below Mach 1. A similar incident would occur in 1956 with the X-2, which killed pilot Milburn Apt on a flight that reached Mach 3.196. An engineer on Becker's team named Charles McClellan came up with a solution. Instead of using a thin vertical stabilizer, a wedge-shaped design was incorporated. This would go on to become one of the X-15's most distinctive features and actually increase stability at higher airspeeds. In April of 1954, just a month after the request from NACA, the Becker Group presented their research airplane. Following the presentation, further wind tunnel testing by Becker, McClellan, and the team helped determine the position of the horizontal stabilizers, which were angled downward for the optimal effect. With a working design concept, NACA shared the results with the Air Force and Navy in August of 1954, and the three parties agreed to conduct a joint program to develop and produce the new research airplane. Interestingly, by this time there were only two major performance-based requirements: attain an altitude of at least 250,000 feet and a maximum speed of at least 6,600 feet per second. Aside from these performance requirements, there was a 30-month deadline to produce the aircraft. By December of 1954, the Air Force reached out to over 10 aircraft manufacturers to submit proposals for the new aircraft. Referred to as Air Force Project 1226, with aircraft designation X-15, in the end, only 4 companies submitted proposals: Bell, Douglas, Republic, and North American. After reviewing the 4 designs, the North American entry was selected as the winner. Interestingly, North American, unaware that they had won the competition, formally asked the Air Force to withdraw as they were working on developing the YF-107 and could not meet the proposed timeline. Upon learning of an 8-month extension on the timeline, North American withdrew their letter and were awarded the contract. The North American design closely resembled the prototypes that Becker's team had proposed, with some key innovations, including all-moving stabilizers, which removed the need for aileron hinges that would cause multiple hypersonic shock waves, a fuselage skin that also functioned as the sidewalls of the oxidizer and fuel tanks for the XLR-99 rocket engine, and a redesigned tail. The original, wedged-shaped tail used split flaps that would extend to provide stability at high speeds. However, it was found that the weight penalty from the actuators caused a shift in the center of gravity, so a solid wedge design was developed by North American and Becker's team, which had deployable speed brakes. Throughout the X-15 project, the tail would be redesigned several times. During the build phase, several scale models were tested and evaluated before a final production version could be decided upon. This included low-speed wind tunnel testing at the other facilities and included outdoor drop models to test glide characteristics. Additionally, extensive testing with models was conducted, focusing on the critical moment of separation from the NB-52 mothership. To train the pilots, a 5 degree of freedom analog simulator was used, which tested flight regimes following the burnout phase to simulated altitudes of 180,000 feet. Interestingly, the instruments had to undergo specialized testing as well. The X-15's rocket engine used ammonia as fuel, and there was concern as to the corrosive effects the ammonia would have on the aircraft instruments. To solve this, the Instrumentation Research Division, or IRD at Langley, tested the instruments in a chamber which had 50% humidity and a 50-50 mix of room air with ammonia. The test was run for 360 hours to prove there were no complications. The IRD also developed an interesting instrument for the X-15, a pitot pressure and flow direction sensor which became known as the cue ball. In traditional aircraft, the pitot tube is a device that protrudes from the aircraft and helps measure airspeed along with a static port. Because of the extreme forces that the X-15 would encounter in hypersonic flight, a solution would have to be designed. Using a sphere made of Inconel X with 4 ports drilled out, servos would keep the sphere oriented so that pressure was equal on all 4 ports, allowing both pressure and airflow to be measured. To test the cue ball, it was placed directly behind an F-100 Super Sabre engine and the afterburner was lit. Additionally, in order to provide maneuverability at extreme altitudes where aerodynamic forces were no longer responsive, small, low-thrust rockets were mounted at various points along the wingtips and the nose. Furthermore, the X-15 was powered by the world's first large rocket engine capable of both being restarted and throttled in flight, the Reaction Motors XLR-99. Since development of the XLR-99 was behind schedule, the initial flights of the X-15 actually used 2 XLR-11 engines, the same type engine that powered the Bell X-1 on its historic supersonic flight. In the end, there would be 3 X-15 aircraft produced and flown, each being designated X-15-1, X-15-2, and X-15-3. And finally, in 1958, NACA became NASA, the National Aeronautics and Space Administration. Before the X-15 actually flew on its own, there were several captive carry flights where the X-15 would stay attached to the NASA NB-52. This was done to calibrate the X-15's instruments and test the handling characteristics of the NB-52 and X-15 pair. Next was the glide flight where the X-15 would be dropped from the NB-52 and glide down to a landing. On June 8, 1959, the first flight of the X-15 took place, piloted by Scott Crossfield in the X-15-2. This was only 44 months after North American had won the contract and just 8 months after the proposed 36-month timeline, a vast improvement compared to the X-2. The glide flight was successful and the stage was now set for powered flight. Due to the nature of the X-15's long flight path, several tracking stations were set up and multiple emergency landing sites at various dry lakes were identified and tested to ensure they could handle the X-15 should the need arise. The first powered flight of the X-15 occurred on September 17, 1959, where the X-15 reached Mach 2.11 and 52,341 feet, or about 16,000 meters. During the next flight, on November 5th, the X-15 had its first in-flight emergency. After release and during the engine start sequence, a chamber in the lower XLR-11 engine exploded, which started a fire. This caused Crossfield to perform an emergency landing at Rosamond Dry Lake, with the resulting hard landing breaking the fuselage in half. Crossfield walked away from the landing, and X-15-2 was back in the air 3 months later. Meanwhile, X-15-1 continued flight tests, and it is important to note that the initial flights and tests were conducted by North American before being accepted by the Air Force and NASA. By February of 1960, the X-15s passed pre-delivery inspection and were formally turned over to NASA. For the next 6 months, NASA test pilot Joseph A. Walker and Air Force Major Robert M. White would alternate flying the X-15-1. During this time, the third X-15 was equipped with the XLR-99 engine, which was finally ready for testing. Once again, Crossfield was tasked with testing the X-15, and during a ground run of the XLR-99, a shutdown and restart procedure was performed. During the restart, an explosion occurred that destroyed the X-15 after the wing and threw the cockpit and Crossfield in it 30 feet forward. Somehow, Crossfield was not injured. The cause was found to be an ammonia tank pressure regulator which failed to open. This was soon corrected, and X-15-3 would be rebuilt. In the meantime, X-15-2 was fitted for the XLR-99 engine, and the first powered flight with the new engine occurred on November 15, 1960, with Crossfield once again at the controls. Over several test flights, engine throttling, shutdown, and restart were all successfully demonstrated, with the last of these flights taking place on December 6, 1960. This would mark the last flight by North American and Crossfield. Crossfield himself had an amazing career. Aside from his exploits in the X-15, He was a World War II Navy pilot and the first person ever to fly Mach 2 in the X-2. Now under Air Force and NASA control, the X-15 flights would continue, and generally speaking, 2 mission profiles were flown, one for maximum altitude and one for maximum speed. Ultimately, the program would total 199 flights and run until October 24, 1968. During this time, speed and altitude records were set and then broken. By the end of 1961, the X-15 had flown at Mach 6 and also flown over 200,000 feet. By the end of 1962, flights over 300,000 feet were routine. Heart rates for the pilots were found to vary between 145 and 185 beats per minute. And at Mach 6, the X-15 experienced 8 times the heat load compared to Mach 3. On 2 occasions, the outer panels of the X-15's glass windshield fractured due to the heating loads. This was solved by changing the cockpit frame from Inconel X to titanium and using high-temperature alumina silica glass. Another change made during flight testing had to do with the ventral tail. During the early flights of the X-15, the lower section of the ventral tail had to be jettisoned prior to landing in order for the landing skids to contact the ground. It was discovered that during the reentry phase, the X-15 had to fly at angles of attack of at least 17 degrees. However, the large ventral tail posed potential rolling problems. The ventral tail was shortened, and this allowed the X-15 to safely operate at angles of attack above 20 degrees, and eventually even 26 degrees at speeds of up to Mach 6. These re-entry characteristics would turn out to be similar to those flown by the Space Shuttle. By 1962, North American approached NASA and the Air Force and proposed taking one of the X-15s and modifying it as a testbed for hypersonic engines. The flight schedule was full and the offer was initially shelved. However, in November of 1962, X-15-2 was damaged in a landing accident which seriously injured pilot Jack McKay. McKay would recover and continue to fly the X-15. However, since the aircraft had to be repaired anyway, the Air Force authorized it to be rebuilt as the X-15-A2. The X-15-A2 was lengthened by 29 inches at the fuselage, with the extra volume intended for a liquid hydrogen or LH2 tank. The tank could be replaced by other equipment if needed, and was actually used to house cameras to test reconnaissance concepts. The X-15A2 also had the capacity to carry additional propellant tanks to provide more powered flight time for the XLR-99. By 1964, the A2 was flying, and in 1966, after jettisoning the drop tanks at Mach 2.27 at an altitude of almost 70,000 feet, Pete Knight set an unofficial world speed record of Mach 6.33. Concurrently, a non-functional dummy ramjet was attached to the A2 to determine the best design in anticipation for continued flights into the 1970s. By this time, the X-15 was flying almost routinely at Mach 6, and the next goal was Mach 8. In order to reach these incredible speeds, which would result in even higher temperatures, an ablative coating would be used to cover the X-15. The idea of coating an aircraft with a heat-absorbent material was already being investigated as part of the early stages of the Space Shuttle development. The X-15 made for an ideal test vehicle. The Martin Company developed a material called Ma25S, which would provide protection from the estimated 2,000 degrees Fahrenheit temperatures expected at Mach 8. The coating took 6 weeks to apply, and an eyelet was installed on the left cockpit so the pilot could see during the landing. In March of 1967, X-15A2 flew with the ablative coating, the goal of being familiarization with the handling qualities of the new configuration. Piloted by Pete Knight, the aircraft reached Mach 4.94, which set the stage for A2's next and final flight. On October 3, 1967, Knight dropped away from the NB-52 and into history. He lit the XLR-99 engine and ran it for 140.7 seconds. The flight reached an altitude of 102,700 feet and a speed of Mach 6.7, or 4,520 miles an hour, a record that still stands over 50 years later. The ablative coating had worked, however, areas around the dummy ramjet experienced much higher than predicted heat levels. This increased heat caused 3 of the 4 explosive bolts connecting the ramjet to the pylon to detonate, with the ramjet actually separating on the downwind leg of the landing pattern. The entire flight lasted 8 minutes and 12 seconds. Upon post-flight inspection, it was found that the ablative coating had actually prevented cooling at certain hotspots. The damage was so bad that one program engineer stated, "If there had been any question that the airplane was going to come back in that shape, we never would have flown it." These findings and subsequent studies led the Space Shuttle program to pursue forms of metal and ceramic shingles instead of the coating used on the X-15. Ultimately, a total of 12 pilots flew the X-15, each with incredible careers in aviation. For the pilots who flew above 50 miles or 80.5 kilometers altitude, the Air Force awarded them astronaut wings. Of the 12, 8 pilots accomplished this: Joseph A. Walker, Robert M. White, John B. McKay, Robert A. Rushworth, Joe H. Engel, William J. Knight, William H. Dana, and Michael J. Adams. Unfortunately, one of these high-altitude flights would end in tragedy. On November 15, 1967, in what was his 7th X-15 flight, Adams would reach a peak altitude of 266,000 feet. Performing a planned wing-rocking maneuver to allow an onboard camera to scan the horizon, the X-15 began to drift off-heading. The ground controllers did not have heading information and were unaware of the problem. After further heading drifts, the X-15 entered a Mach 5 spin. Adams recognized that he was in a spin, but there was nothing known about the X-15's hypersonic spin tendencies. Adams was able to recover from the spin at 118,000 feet, but then the X-15 went into an inverted Mach 4.7 dive at an angle estimated to be between 40 and 45 degrees. The dive was recoverable, but the MH-96 adaptive control system prevented pitch reductions as dynamic pressures increased. Passing through 65,000 feet, the X-15 was traveling at Mach 3.93 and experiencing 15 positive and negative Gs vertically and 8 Gs laterally. The aircraft broke up 10 minutes and 35 seconds after launch. X-15-3 was destroyed and Adams perished. Lessons learned from this tragic accident led to the installation of telemetered heading indicators in the control room, and X-15 pilots were screened for vertigo sensitivity. Adams was posthumously awarded the astronaut wings. And as for the 4 other pilots, Scott Crossfield was a North American pilot and therefore ineligible for the wings. Forrest S. Peterson was the only Navy pilot to fly the X-15 and made that first emergency landing at Mud Lake. Then there was Milton O. Thompson, who flew the X-15 14 times and reached a top speed of Mach 5.48. And Neil A. Armstrong, who didn't fly the required altitude in the X-15 for the astronaut wings, but would go on to become the first man on the moon during the Apollo 11 mission. It is difficult to overstate the impact the X-15 had on aviation and spaceflight. A program which initially called for flights of Mach 4 to 200,000 feet and surface temperatures of 1200 degrees Fahrenheit exceeded all of its design goals. The X-15 achieved Mach 6.70, altitudes of 354,200 feet, and recorded temperatures of 1,350 degrees Fahrenheit. The X-15's re-entry flight experiences led directly to the systems and techniques used by subsequent spacecraft, including Mercury, Apollo, and the Space Shuttle. Aside from the speed and altitude performance, an often overlooked contribution of the X-15 are the breakthroughs that were made in bioinstrumentation. Pilots were closely monitored on biomedical parameters such as heart rate, respiration, and EKG readings. The X-15's findings showed that the theoretical limits of what a human could endure could be expanded, and gave researchers the confidence to proceed with the manned Mercury flights. The X-15 program is also credited with developing the first practical, full-pressure suit for space operations. To assist in re-entry, the X-15 also implemented a Stability Augmentation System, or SAS. While the first 2 X-15s were equipped with simple fail-safe fixed gain systems, the third X-15 was equipped with a triple redundant adaptive flight control system. And if that sounds a little familiar, it's because this flight control system would evolve into what will become known as fly-by-wire. The X-15 did not have a pure digital fly-by-wire system, but its implementation would be developed and used on an entire generation of aircraft, such as the F-15 and then the FA-18, which would evolve the concept even further. Neil Armstrong once called the X-15 the most successful research airplane in history. As incredible as these achievements were, the X-15 could have done more. The program had planned flights with hypersonic engines among other experiments, but was retired due to budget cuts. Upon hearing the news, pilot Pete Knight commented that he would have pushed it to even further speeds if he knew it was the last flight, hinting that we never got to see the true maximum speed of the X-15. And perhaps its lasting legacy can be summed up by Crossfield, who stated the X-15 was one of the few aircraft that caused grown men to cry upon its retirement. Today, you can find the 2 remaining X-15s at a couple of museums. X-15-1 is at the Smithsonian, where it was on display for over 43 years. However, in August of 2019, it was put into storage as part of an ongoing 8-year museum renovation project. X-15A2 is on display at the National Museum of the Air Force in Dayton, Ohio. To me, the X-15 embodies our desire to go faster, higher, farther, and to continuously push our boundaries as to what is possible. What do you think? Was the X-15 the most important X-plane? Should it have continued flying into the 1970s? Let me know in the comments below. Thanks for watching. If you enjoyed this video, go ahead and subscribe and click the bell for notifications. I'm working on an entire series on all the NASA X-planes, so stay tuned for more. Stay safe, and see you next time.